Thank you, Greg. So yeah, it's my pleasure to talk about large behavior models for manipulation. So I used to work in self-driving. Now I'm doing something much more dangerous, is humanoids with knives. So you'll see, I'll show you a video quickly about knives. But yeah, a little bit about me. I'm an explorer, so I did my PhD actually here with Cordelia. Then I worked with Florent at XRCE before it was NAVER Labs. And then I moved to Silicon Valley to work on self-driving cars, robotics, large-scale training of models, and all that kind of stuff. Then I spent a little bit of time as an entrepreneur, as a founder, became a VC, and now I'm back at TRI, essentially to work on a new initiative. And actually what's really important is that the work that I'm going to show is all the credit goes to Rusty Drake, Ben Birchfield, Rajesh Ambrus, like my colleagues at TRI in the LBMC team. So really, when I say we, I mean them. All the credit goes to them. And so for me, it was a little bit interesting. I've done kind of a bit of an interesting and fast-paced journey. And the reason I came back is because we got really excited about new initiatives around a new type of product, which is humanoids and dexterous manipulation, because I think it's really the bottleneck for these robots to be useful is to be able to do stuff with their hands. And I think what I'm going to show you today is the evidence that convinced us really that there was something there. There was signal. It's not hype. It can actually really work. And thanks to something we call large behavior models, where we can learn manipulation from data. And so basically here what you're seeing is, I promised it, robots with knives. So what you have here is essentially a robot foundation model. This is what an LBM is. I'll give you a little bit more details. And we just trained for about 500 tasks. You prompt it, please core an apple, and it will do things. It will core the apple using sharp things. You don't want your fingers there. And you'll see, so it's very dexterous. It's bimanual manipulation. Yes, it will unsheath a knife. I'm actually scared to use that knife myself. It's very sharp. And then it's going to do a very long horizon task. And once again, it's a neural network that's trained end-to-end. There's no task planning, etc. It's just one long task. And it will do it pretty safely. So it's all autonomous. Right now, we're just accelerating a little bit so that I don't, it's cool. I'll have a longer video on some other tasks at the end while we have questions. It's not perfect. So what you'll see here is that it drops the towel, but it has recoverability. And here, this is really, like, pay attention. This is beautiful. Like, for a Japanese company also, like, putting it back. This is really hard. Like, I'm scared to do this myself and, like, just put the knife in my finger and stuff like this, right? So this was not a humanoid. This was just like a tabletop setup with bimanual arm. But we've had a collaboration with Boston Dynamics. And it's the same neural network that's basically doing tasks. Like here, it's taking parts from the Spot robot and putting it from one bin into the other bin. Yeah, I'll let it roll a little bit. But you see, it's a full-scale humanoid. Same thing, what you see is not perfect, but it has recoverability in the policy. So it's learned how to try again. Even if you have a mean Boston Dynamics person with a hockey stick, they like to do that to their robots. But our AI, not disturbed, does it again, tries it again, has infinite patience, and can do these complex tasks. It's very cluttered, yeah, this is again 1x speed, so this is not sped up, robust to again mean humans. Okay, I can show you more videos later. But so how do we do that? What's the system behind this? How's this? And so as I mentioned to you, it's essentially a language condition visual motor foundation model that is trained by imitation learning on large-scale multitask data sets that consist of action-level demonstrations. So here in this case, there's tons of excitement about data. We're going to talk a little bit more about like different options in the data, but like everything here is essentially see what people have done with language and people have done with vision. We're doing it with robot data, right? So just robot data. And so we do have two parts of the model. So the main part of the model is a DIT model, is a diffusion transformer. We can talk about the details if you want in terms of the size of the latent space and all that. I think there's 8 blocks in the model. As the input, you also have, so you have two images, two time steps that are fed through a clip encoder. I mean, at the time of this paper, then now you can use much better models and bigger models. Same thing for the text instruction. So what's funny is that there's a bunch of data sets for which, that not the data sets we collected, but some other data sets we use, there's no text instruction. So what do you say? You say, do something useful, and that's it. That's your language conditioning. You have other signals like end effector pose and type step, because this is a diffusion model. During training, we fine-tune through the visual feature extractor because, of course, we want to adapt to the visual modalities of the data that we collected. It's shared across all camera inputs. We do keep the language feature extractor frozen, but we learn a projection layer on top of the language features. An important thing, because this is outputting actions, is the way we parameterize the action space. And so one of the things that the community has found for this kind of end-to-end models is predicting multiple time steps into the future. So we predict 16 time steps of roughly 20-dimensional actions. We just execute 8 at inference time, and then we rerun the 16 predictions. The reason I'm mentioning this is going to be an important detail when I talk a little bit about some engineering gotchas we found out. And all policies are run at 10 hertz, which is, I think, enough for the tasks we talked about. You can imagine there's certain tasks you need to move faster than this, but 10 hertz is what we've used. So talking about the data, so Cordelia yesterday, I think I'm going to cite both Cordelia and a few other people here. Mentioned that indeed the data is the most important thing. And what I will say a specialized version of that argument, which is post-training data, the top of the pyramid, is really what we think is the most important. The reason is, so of course, we don't train from scratch, right? There's always this initialization that you get for free now, essentially. It's a commodity. It's like the internet AI priors. It's models, pre-trained models, or even just training yourself. We know how to do this now. The interesting bit starts, and this is the robot-specific bit is above that. So again, pre-training data. There's lots of different pre-training modalities. I mean, you've heard of world models. You can think about ARIA glasses. There's tons of stuff there, tons of options being explored by the community. We have some specific ideas there. In this paper, it's all robot data, again, because we want it to be in a kind of a clean robot foundation model story. So you need lots of it. It's pre-training data. So this is a bit of a challenge when it comes to robotic data. But I think eventually it will be commoditized, because we will be able to mix in different types of modalities there, including things like Mark showed, with Yumi and other devices that are not robots, but are kind of closer than just YouTube videos. What's large in your case? Sorry? What's large in your case? So it's 1,700 hours of pre-training data. It's on the next slide, I think, or subsequent slide. So it's not that large. If you think about like just video stuff, etc., like now you have people that have 100,000 hours or 200,000 hours of data, but it's not robot data doing useful tasks. It's like people with gloves or stuff like that. So the most important, again, data, I think, is really the top of the pyramid. And so this is where actually you train the robot to do something useful. And that, I think, is like the very interesting difference, let's say, from self-driving. My self-driving days is that driving is just really one task. I mean, it's like a lot of scenarios. It's very complicated, but essentially it's just it's two steering and accel and stop. Here, coring an apple, fixing an iPhone, this is very different things. And so depending on what you want the robot to do, this is how you tell the robot to do, how you teach the robot to do certain things. And it cannot invent it. It can learn and generalize from text. And again, this is language conditioned, but it has to know what you want it to do. And this is really hard to get, because now you have to teach the robot, right, to do the tasks you want to do. And so the way we do this is via teleoperation. And so obviously this is something that is hard to scale. So that data is very important, high quality, and that's what we spent a lot of our time on collecting, again, to be able to convince ourselves that that data is valuable indeed, right? If you go through the effort of teleoperating, etc., it's like you want to make sure that this is a wise allocation of your resources. You get the most bang for your buck. And so our own high-quality data consists of a total of 545 hours of real robot data over 532 tasks. That's a total of 64,000 expert demonstrations, right? So that's a lot of robot data. We also use other data sources. So there's a filtered subset of the OpenX embodiment dataset, which is a big kind of like a collection of multiple different robotics datasets in the community. So it's cross-embodiment, etc. We batch balance the things because we think our data is just really high quality, and what we see is it's really useful. But we also, what you can see is we also have a little bit of sim data at training time and a little bit of also Yumi data. Which is this handheld device that Ben and Chengxi, Ben Birchfield, Chengxi, and others have come up with. The reason, I just outlined very briefly, a very important reason for why we have a little bit of sim data training time and we do co-training between sim and real world is actually for a reason that Annie mentioned earlier, which is evaluation. Evaluation is really hard, I completely agree. It's actually much harder, and now we know how to train models. We know how to get data. It's kind of a resource allocation thing, but like evaluation is just a really, really hard problem. And so we co-train with a little bit of sim data for one specific purpose, which is it enables us to trust our sim evaluation. Because when you evaluate robot policies, we know for a fact, it's just known in the community really well, both empirically and theoretically, that open loop evaluation does not necessarily correlate with closed loop evaluation, right? And especially I've shown you behaviors where you have recoverability, you have like lots of rich interaction, and so you need to evaluate a policy. When you add that level of task and that level of performance, it's about closed loop. And the only way we know how to do closed loop simulation, closed loop evaluation, gave the plot, is simulation. But you have to trust your eval. You have to trust your sim. So one way is you learn the sim, and you learn the sim and the real world model and the policies at the same time, and both improve over time together. And it's kind of like it's a journey. But for certain tasks where you want to actually know for sure you're gonna deploy, and you can model it, then having a really powerful simulator enables you to get really strong confidence in those results before you do the more the real world eval, right? And so that's something that the team at TRI, in particular Russ T. Drake with the Drake simulator, and at MIT and at TRI have done a lot of work on really good, really accurate simulation, such that not so much for data generation, but so that we can evaluate at scale in a way that transfers to the real world. So that's the evaluation setup we have. Oh, by the way, I told you everything about the model. Now there's nothing more about fancy machine learning. It's going to be all boring eval and all data and no fancy architectures anymore. Because what we found is that that's what matters most. So we have, yes. Okay, that's an important thing. So there's 1,700 hours of pre-training data. But then in eval, we have two different types of evals. We have evals on seen tasks and eval on unseen tasks. So what we do for evaluation is we do fine-tuning on a new task, and that task can be either seen at pre-training time, or it can be completely different, never seen before. And so what you see here is you see that there's 16 tasks. So for evaluation in sim, we have 16 seen tasks, which were seen at pre-training. So meaning we just do a post-training on tasks we've already seen during pre-training. And then there's 8 unseen tasks. What's really important, and I'll show you why a little bit, is that you have to randomize initial conditions. If you want to do like rigorous evaluation, you have to do rigorous statistical testing. And so we're basically testing both in distribution and out of distribution generalization. One of the key, wow moments from ChatGPT was really this zero-shot generalization, which is the signal, the source of signal for real robustness in generalization. So we do carefully analyze in and out of distribution. And in sim, again, one of the big benefits in sim, if you can trust your simulation, just a very important caveat and a lot of work to go there, you can evaluate a lot. And so we're doing 47,000 simulation rollouts in this case, which is, again, a lot. And in real, we have, because it's much, much more costly, we do less. So we do 3 seen tasks and 5 unseen tasks. We do 50 initial conditions and 1,800 real-world rollouts. One of the particularities I will say about the real-world evaluation is that the unseen tasks are really, really different than the pre-training one. So this is really far out of the pre-training distribution. So this is like a very, very big challenge. internally they're calling this like extravaganza, you know, like there's tasks which are like, you know, like the bike rotor task, for instance, which is the last video I'll show at the end, which are really, really different. Okay, so we evaluate the policies, what do we want to evaluate? And so there's some hypothesis we wanted to convince ourselves, again, because doing robotics is very hard, it's very expensive, so, and not just in GPUs, but in actual time, physical time in the world, and people doing stuff. So we wanted to convince ourselves that the scaling laws and all this kind of stuff transfers for these robot foundation models. So the first one is that new tasks can be learned with less data, right? That's the benefit of pre-training, is that now you say, I want to do this, my robot to do this new task. Is the pre-training helping me get to that faster? The second, of course, is we want that pre-training just helps performance in general, even for tasks you've already seen. You just want to get better at them. And then third is we want to assess whether policies are indeed more robust to distribution shift, which is, again, the fundamental property of these foundation models. So there are a lot of results in the paper. I just want to highlight two quick plots. So results are somewhat task dependent, but the trends are pretty clear across the board, both from simulation and for the real world. So on the left, what you see is our simulation results. So again, the evaluation is we're fine-tuning pre-trained LBM into task-specific specialists. And what we're seeing is that the specialists that are fine-tuned from the pre-trained model always outperform the from-scratch trained models, given a certain amount of fine-tuning data. And what we can show also is that we can achieve, like with the pre-trained model, we can achieve the same level of performance as training from scratch, but with 3 to 5 times less data. So again, that first hypothesis I talked about, pre-training enables you to get faster to better performance. Like faster to similar performance, or get better performance. That seems to be true in simulation and in the real world. So you have the scaling laws on the left for the simulation, and on the right you have these evaluations for the real world. So if you're not too familiar with violin plots, this is basically just a representation of the distribution over the rollouts. I'll explain to you why it's important to look at the whole distribution, because expectations hide a lot of things. And then the other thing is this letter notation. If you see the same letter, like for instance for the bike rotor install, you see a AA between the single task trained for that task and then the fine-tuned LBM. That means it's not statistically different for that task. And if it's like AB, that means this is statistically different. Like the separation is statistically meaningful. Yes, on the right side, these are the real world tasks, and the trains are the same. And as I mentioned earlier, what's particularly interesting for the real world is like we have less of it, but we made it much more challenging, is that even for tasks that are way different than the pre-training ones, like things that are pretty out of distribution, we find that yes, foundation models provide that benefit of better generalization to these really different tasks. And so this was very reassuring to us doing this. There's like months and months and months of efforts there, and then a bug, and then you redo it, months and months of efforts. And because it basically convinced us that foundation models for robotic manipulation, they might actually follow, they might not be fundamentally different than foundation models for language and vision. So a similar playbook with all these adaptations that I talked about might actually play out. So it might be worth the effort. So here's an example result. So what you see is on the right is this task trained, so end-to-end, which is like preparing a breakfast tray. And on the left is the task where with LBM pre-training. And so obviously you'll see, so it's one long task, so it's just to show you how long horizon these tasks are. This is not sped up. But you see already there's a problem with collisions between the two glasses. If there was actually liquid in there, it would be already a big mess on the right. But you see you have some also kind of like this behavior of airballing that's happening right there with the arm on the left side without LBM, where it thinks it grasps an object and then it just does it, but it has nothing. That's a behavior that we see that with LBM happens much less frequently. Yes, and like there's other kind of like failure modes that you see on the right that you don't see on the left. On the left, it's not perfect, but again, like when it fails, it has like there's this emerging property of like really high recoverability from these failures. Some videos that I don't show here, but like in the example without LBM, for instance, we just like fling the toaster out, etc. So yeah, that's the real world. It's like, don't do this in your bathtub. Okay. So pre-training really helps, especially on the end, it's recoverability behaviors. So, okay, I showed you the traditional plots, actually with a little bit more rigor there with the distribution and etc. I'll explain to you why we had to do this. And I showed you some examples, but actually one thing that I want to emphasize, and that's actually to me was what made this work really different than most other works in robotics, is the level of rigor. And in robotics, we very often do demos and things like this, and then we get convinced, oh, the robot could do it. It's like proof by existence, It's like amazing, it can do it. But actually, you can be fooled, like very easily fooled, especially now with this, probabilistic systems. And so we found, and this work is that we had to raise the bar in evaluation rigor a lot, so that we don't fool ourselves. And as Feynman said, we're the easiest persons to fool. I mean, not us, but yourself. So just a quick, brief, like high level is like, for instance, as a machine learning researchers, we're thinking like architecture really helps, and yes, it does. But many architectural changes that we're getting excited about early on turns out to, be mostly up in the noise. I'm sure any PhD advisor has had experience with first meeting with students saying, yes, this is the way. Next meeting with students, like, actually, no. and so when you invest a lot of time and money, etc., you want to say, okay, how do we avoid that situation? I'm sure it happened to me with Cordelia even back in the day. And so how do you differentiate the changes that are meaningful or not, and what you should focus your attention on? So again, this is just the actual example scenario from experiments from a while back. You start with task A, you're like, yes, the yellow bar, it's all anonymized or whatever, but like yeah, yellow bar is the method, is my method. Let's go, let's, 2 hours before the deadline. Task B, yeah, yellow bar is better, but yeah, wait, happened. Blue now it starts to be like much better, and then it's like, wait, no, now blue is actually better than yellow. So these are real bar plots, right? So whenever I see a bar plot, by the way, I get huge red flag. Like, it's like same thing is that people talk to you about robotics, they only do simulation experiments. I was really glad, like, Cordelia had real world experiments. I was like, yes, whew. Like simulation on the experiment, huge red flag. Bar plot without error bars, huge red flag, because this, right? And don't do this to yourself. It's just gonna hurt. And so. Yes, exactly. Table of numbers, like just longer than your arm, like same thing. I'm just scared for you. I'm like, this is gonna be bad. It's gonna hurt. And so what happened there? Small sample size, classic, right? Like high variance, uncontrolled initial conditions. You're in the real world. You're doing these experiments. Cross-task variance. That's actually the very big deal. I think in manipulation, where it's like different than driving in other scenarios, is like it's not only about robustness to visual changes or robustness to the behavior of other agents. And it's robustness to your robot messing up, right? Or it's robustness to this task turns out to be very easy for robots. Why is everybody folding clothes with robots? Because you can. Because the robots turn out to be really good at this. Why aren't people doing origami? If you were at a choral, for instance, you would see like a master, like a takumi, a master craftsman for origami, and then you were seeing no robot doing origami. Why? Because it's really hard. And now you have two tasks. Imagine you have folding clothes and origami in your data set. Like one is like 99%, robotics is solved. The other one is like 0.1%. There's no hope, right? And now you're reporting an average metric across those things. Not sure. It doesn't leave a good taste in your mouth, right? And so just talking a bit more rigorously in terms of statistics, we're talking just about power, which I just lost. I guess I'll do the Andrea trick. Yes, but maybe I don't have the Andrea touch. No, I do. Okay, good. Okay, so here we're talking about statistical power. So we're doing like hypothesis testing. So here you show So basically statistical power as a function of sample size. Remember, sample size in our case is actual robots interacting with the actual world, right? So of course you want large N, you want large data, but like here, large data means time, like spending on your robots, like actually breaking it, fixing it, and all this kind of stuff, right? And so what you see on the x-axis is success rate, and what you see on the y-axis is the confidence interval width. So what it means is basically that, so we selected in this paper, there was particular, because there's such a task dependence, right? Like the results are really dependent on the task, if you, as I mentioned before. So you're trying to aim when you're designing a benchmark, like Mark talked a lot about benchmarks design. So a good benchmark is a benchmark where you're basically at around 50% task success rate, because that's the highest information you can have. If you're too low, nothing works. If you're too high, everything works. So you want to be somewhere in the middle where you have a lot of kind of variance, and that's where you can have the most, like the most entropy, the most information gain, and all that. So if you're around there, where it's just kind of where we want to be, and then you're basically increasing from, like, let's say 10 rollouts to 20 rollouts, right? And if you're in that kind of ballpark, what happens is you see that if you have two methods, or if you have student A, student B, or policy A, policy B, and they're within 15% of each other, you can't tell them apart. One tells you I'm 15% better, is like, said, I don't trust you. I don't believe you. Because you can't prove to me that it's statistically significant. So you need to work harder. You need to do more. Okay, great. Do more. It's expensive, more time with the robots, more robots parts break, all of that stuff. But now, if you do this, sure, you can get actually to a confidence interval width that's kind of around the 30, 20%, something like this. If you do sim, single task, right? Same thing. But it's still not great. You can start to disambiguate, distinguish a little bit more between methods. And then where it's really starting to, like, you squeeze the juice again of robotics, which is like you can have more tasks. It's not just one task, right? Now you can start to get, like, you know, into a realm where you can talk with some amount of statistical confidence about the results, about saying it's better, or, you know, like, you know, not in the sense of like we have the best robots, look at our video, but in the sense of like, is it actually working better? Should I put that on the robots tomorrow because it's better than today's? Still not great, but it's actually much more powerful. But it's a lot of work. You have to do a lot of tasks, you have to do a lot of rollouts. Now, another thing that's actually everyone in computer vision is very familiar with is data augmentation, domain randomization, all this kind of stuff. So as I mentioned, 200 different variations. So we ensure diversity with a lot of randomization. Again, if you work at a university, befriend a statistician. They need some love too, and actually we can benefit from their wisdom. And so doing kind of rigorous statistics, but even just like, I mean, everybody's using Python, right? So if you use libraries like Seaborn, Pandas, all this kind of stuff, they have this natively, right? So don't hurt yourself with just showing one bar or one expectation. Use violin plots. It's like just literally one line of code. But you have to know a little bit about statistics to do this right. And again, very easy to fool yourself. You know the reproducibility crisis in a lot of like other sciences, etc. P-value hacking, etc. Like, we're not immune to that, right? It's not because it happens to others, it doesn't happen to us. So just be very careful with statistics. And the other thing that I will say is that I showed you an example, right, of saying like, oh, look at this example, it's better than the other, etc. I did show you like general distribution results first, but be very cautious with examples and over-indexing on examples, because if you look, I show you the breakfast tray without LBM and with LBM is better, look at all these behaviors, and it was. But actually, you could probably sample from the distribution, maybe sample in a very biased way if you like certain method or other, if you have an agenda, right? Or even not. And you can basically go into a part of the distribution where you can say whatever you want, right? Because those differences are statistically significant, but you can find a sample that completely flips the conclusion, right? So yes, that's the big lesson in robotics. You can't avoid the pain. You just have to pay it. But all that pain, all that investment actually is tremendously freeing, because now once you know you're not fooling yourself, now you're you can iterate really fast and move in a direction with confidence, right? And start to say, I'm going to hire annotators. We're going to be, you know, peeling potatoes. Let's go, you know, because I know that I can evaluate my methods properly, right? And so you can start running as fast as you can, And so this is, but again, there's so many startups, so many companies that are now just saying, I'm going to go as fast as I can on the data, because the data is really the most important thing. So I'm just going to scale the data. And so then you're going to have this huge fights between, REI is the way to go, no, world model is the way to go, video prediction, et cetera, et cetera. So it's like all great. And I think this is amazing that there's such diversity and such debate in the community for this. We are much more focused on the evaluation. Again, like that's, I think, a bit the difference between machine learning people turning roboticists to roboticists turning AI people, is that the roboticists turning AI people, they have all these battle scars, right? And they have all this kind of pain that they went through, and so they get a little bit paranoid. And so they're embracing machine learning. Maybe it took them a little bit of time, but they are really very rigorous on the eval. Again, for all the reasons that I talked about, because robots do break. And so we put again a lot of effort in rigorous evaluation. There was all this kind of work earlier in the simulator that really paid off. It was a major workhorse for us. We run 4.5 million simulation rollouts, right? So imagine this. In the real world, it's impossible. You just cannot do it. It's like saying we need to drive 1 billion miles every time we have a new release. Oh, we have this new idea for data augmentation. Yes, 1 billion miles, sir. Oh, you know. So you need the simulation. I mean, it's obvious you need simulation, and there's different flavors of it. Whatever strikes your floats your boat. The other thing that I will say that is really important, that is not often discussed, but again, it's something that I want to share with the community, and it's again details in the report, is that software 2.0 still has software. Actually, it's most of the letters. It's still software. so engineering is really critical. Learned systems are not magic, and the details really matter. There's tons. And I won't go into the details. And even though LBM is an end-to-end trained model, there's tons of engineering in there. There's tons of prior knowledge. There's tons of structure, right? I talked to you about, like, for instance, how do you encode the action space? That matters, right? That's a big difference. Another one that's probably like very little to do with robotics, everything to do with statistics again and with machine learning, is just data normalization, right? Turns out that architecture, etc. Oh, that flavor of DIT, no. How you normalize your data. That had, it's crazy, but that is one of the things that had the most impact. Another important little detail, care about is safety, right? And so again, like, how do you get robots to do stuff with knives? Either because you don't care, but you're not going to live for very long, or because you trust them, and because you trust your evaluation to actually say, okay, let's give the robot a ceramic knife. And so again, like, you have to have, for instance, basic knowledge about robot control. Like, there's a diff IK in there. There's stuff. It's like not just an end-to-end model. There's actually, it's like on top of every trick in the book in robotics. And if you know Rusty Drake, I mean, that's he brought the old world with the new, right? And it's not just in replacement of. I remember this paper from Andrea, training the old with the new in NFM, right? Or training the new with the old. Here it's the same. It's like there's this idea of, like, it's not either or, it's and. So many bugs found and fixed. And actually, what this even materialized, it's not just like, it's like things don't work with a bug. I mean, everybody that's been machine learning for a while knows that, you can have bugs in systems and they still work. But here, this is like 3 years old. And it works. I mean, this is a diffusion policy. This is single task. This is pre-LBM. This is amazing at the time. Like, it was just like, wow, it can do this. But you see, it's like this, right? It's not great, right? And there was nothing wrong with this, right? There's no bug in there. But it's just like a lot of engineering details, in addition to the pre-training on all the data and the stuff I talked about, is what enabled to not just unlock capability, but just improve performance. Now, one of the most elusive questions is, of course, the right data, right? So far we did all this kind of rigorous evaluation to differentiate into the policies and between the policies and all this kind of stuff. But what we didn't do is we didn't say, well, let's do the same kind of rigorous evaluation for data mixture, building the data mixture, or for any kind of like data set design. Right, so like Ludwig Schmidt had done these competitions recently, right? Data comp LM, all this kind of stuff, right? Which is like the key question is just like, what is the optimal data set, right? And again, because I said it's very expensive to evaluate, it's very expensive to do these design choices, is there a way that you can think about data in a more structured, more rigorous way? And the reality is, we don't know. We don't know. This is the big unknown. I think this is where there's huge question and limits of empiricism. I mean, we need to do this, so we need to spend the investment to do this because it's empirical. But right now, you have a lot of options, as I mentioned. So ARIA, YouTube, gloves, Yumi, cross-embodiment, synthetic data from sim, model-based sim, from learn simulators. I mean, it's going to be a little bit of everything. The question is how much of which, you know, it's like you're making a data soup, and how much spice do you put, and how much chicken broth, how much all of this kind of stuff is like, we don't know. And there's a lot of strong opinions and some very, very big bets based on those opinions. But those bets, I think, are a bit more governed by resource availability than a clear notion of usefulness. If you sit on YouTube, of course use YouTube. If you make the ARIA glasses, of course make the ARIA, use the ARIA glasses, right? And so, but the reality is we don't know. And so you have to kind of like go a little bit on a limb. But where we develop confidence, again, because we've based ourselves on the post-training, we know, and it's more than belief at this stage, we have the evidence that robot data is really the holy grail. There's no alternative to the robot data. There's supplements, again, it's like, but you can't replace, you know, completely robot data. And if you can scale it, I think you have the highest likelihood of success a priori. And the argument is not necessarily one of in-distribution. It is not because it's the closest to the deployment data. I mean, of course, that's a huge benefit, but we do know it's a foundation model. We know from foundation models that diversity is important, you know, to create this kind of robustness to out of distribution that I talked about. I think the argument is actually an argument that Mark talked about yesterday, and that I will rephrase a little bit. Same thing. I'm just going to steal from you know, stand on the shoulder of giants, as they say. The biggest benefit of real robot deployment, even with teleoperation, which is slow, right, and you pay twice the cost, the robot and the person, is task discovery, right? It is task discovery, or I would say more specifically, and this is where maybe a former VC hat, which is product market fit or robot market fit. Right? Because there's such a variance in tasks, and the tasks you choose them. So if you remember, like, you know, RT1, when it came out, it was 700 tasks, but it was like picking up a yellow cube, task 1, picking up a blue cube, task 2. It's like saying ImageNet is 1,000 different tasks, right? It's an okay definition, so not mine, but so the question is like, what is a task? We had this discussion with even Kelton Goldberg, a bunch of people a few years back, and we don't have a clear definition of task. So what matters is that what you want a robot to do. Like, what is it actually that the robot is supposed to be doing? You decide that, and when you design the benchmark, you implicitly decide that too. And so that's and so what we believe is that because it depends on the domain, because it depends on the task so much, deciding the use cases is the most important thing, and that's something we're keenly focused on. So as a conclusion, so LBM, I talked a bit about this large behavior models, which is a robot foundation model. So only in this paper trained only with robot data. We believe in the evidence that we provided, that it's solid. We did the best we could to get the confidence, you know, in the results, to believe that it is a scalable blueprint for manipulation. The reason we developed that belief is rooted in the evidence and the rigor that happened in the course of this project. So again, engineering, really important. Evaluation, like really hard. And of course, data. But that gave us this confidence that we see clear benefits in pre-training. We see the scaling laws. We're capable of handling super complex long horizon tasks like the apple coring and the breakfast tray that I showed you. But again, because we believe we're not fooling ourselves in saying this. And so the question is, as I mentioned, is like what's next? And what's next is like, how do we scale? And I think the important thing is how do we scale with purpose? How do we scale purposefully with data and tasks? And so that's really what we're focusing on right now, is really building generalist robots, because that's, I think, what this general foundation models enable. And we want to be a generalist, but yet we want to be purposeful. And I think the best way to do that is to deploy against real needs. And yeah, and so if you think that too, and if you have ideas, I'd welcome a discussion. Thank you.